Hello everyone. Today we will discuss an important concept in machine learning called multiclass classification. So this is when we need to predict an outcome from multiple categories, not just two. To explain this, let's use a real-world example. So imagine an online shopping company that wants to improve its customer experience. When a customer searches for a product, such as a washing machine, they see several options from different sellers, like example, seller A, seller B, C, etc. So the company wants to predict which seller the customer is most likely to prefer. By doing this, they can highlight the preferred seller as a verified seller, helping customer make quicker decisions, improving their experience, and increasing the likelihood of completing a purchase. So this leads to higher profits for the company. However, this problem isn't as simple as it seems. So in simpler scenarios, such as predicting whether a product will be returned or not, we can use binary classification techniques like logistic regression or decision trees. These methods work well for problems with two possible outcomes, but they fall short when there are multiple outcomes to consider. So in our case, there are four possible sellers for each customer, creating a multi-class classification problem. This means that the task is to predict one category out of several, and traditional binary classification algorithms aren't enough to handle this complexity. So to solve this, we need specific techniques designed for multi-class classification. So in this presentation, we will dive deeper into multiclass classification. We'll explain what multiclass classification is and why it's important in real-world application. Secondly, we will explore multiclass classification methods and discuss performance metrics. We'll address class imbalance data, and finally, we'll summarize key points. By the end of this presentation, you'll have a better understanding of multiclass classification and the tools needed to apply it effectively.
So the classification algorithms discussed so far have primarily focused on binary classification, where the target variable is limited to two possible categorical values or classes. However, there are scenarios where more than two classes are required for classification. For example, when analyzing customer transaction, the marketing team may need to determine the most suitable credit card for a customer, such as cashback, air miles, gas station, or shopping. In such cases, a different approach is needed compared to binary classification. Multi-class classification problems can be categorized into three main types. The first one is the multi-class classification. This involves assigning each instance or sample to one class out of multiple possible classes. Each sample is assigned only one label with no overlap. For instance, a project can be bought from only one seller. The second is the multi-label classification. In this case, each instance can be associated with multiple target labels. For example, when categorizing a movie for advertising, it may belong to multiple genres such as horror, comedy, and thriller. And the third is the multi-output regression. Here, each instance is associated with multiple target variables that may have different properties. For instance, when analyzing a specific project, predictions may include the number of purchases, the number of returns, and the percentage discounts applied to each purchase.
So let's talk now about classifier in multiclass classification. When solving multiclass problems, there are two common approaches we can use. The first one is one versus all classifier, and the second one is one versus one classifier. Each of these methods has its own strengths and weaknesses, so understanding when and how to use them is a key. First example, to set the stage, imagine these two scenarios. An online trading company wants to divide its customer into 5 categories based on how recently they logged into their account. And second, the same company wants to build a recommendation system from mutual funds. The system would suggest mutual funds to customers based on factors like their risk tolerance, investment amount, and other features. Since there are over 100 mutual funds, the system must handle a very large number of classes. So both examples involve multiclass classification, but they are significantly different in the number of classes, which affects how we approach the problem. So about one versus all classifier, the first technique is the one versus all, also called one versus rest. So here's how it works. So for each class, a separate classifier is trained. This is trained. Classifier is responsible for distinguishing its class from all the others combined. During the prediction, each classifier outputs a confidence score indicating how likely a given data point belongs to its class. The class with the highest confidence score is selected as the final product. So here on the diagram, as you can see, we are working with 3 classes. So class 1 is represented by the green triangles. Class 2 is represented by the orange diamonds, and class 3 is represented by the blue crosses. So in the one versus all approach, we create a separate binary classifier for each class. Each classifier focuses on distinguishing one class from all the other combined. Each of these classifiers produces a decision boundary shown as a line in the plot. During prediction, the confidence score from each classifier is calculated, and the class with the highest score is selected as the final prediction from the data point. So this approach is intuitive because it simplifies the multi-class problem into multiple binary classification problems. However, as I mentioned earlier, it can face challenges like class imbalance when where some classes have much fewer examples than others. So now that we understand how the one versus all classifier works, let's see how to implement it in Python using the scikit-learn binary. So for this one, we'll follow a step-by-step process. So the step 1 is to define the classifier type. So the first step is to decide which type of classifier we want to use as our base model. All classifier created in the one versus all approach will be of this type. So for this example, we use logistic regression as the base model. To do this, we need to import the logistic regression class from scikit-learn. So next, about the second step, once we've defined the base classifier, we need to use the one versus rest classifier from scikit-learn. This will automatically handle the creation of multiple binary classifier for each class. So the code for this step is, as you can see on the step 2. Here, the OVR object is our one versus all classifier, and it's ready to be trained on our dataset. So about the step 3, like any other machine learning model, we'll now fit this classifier to our training data. This step ensures that the model learns how to classify the data into classes. So as you can see, the code of step 3, here xtrain is our feature matrix, and ytrain is our target variable. And the last step, step 4. Once the model is trained, we can use it to make prediction on new or unseen data. So the code, the predict function works just like it does for binary classification problems. So here's the code for making prediction, as you can see on step 4. And for this one, X is the feature matrix for the data set, and prediction will contain the predicted class for each data point in the test set. So all this process simplifies multi-class classification by breaking into multiple binary classification problems. So next, about the one versus one classifier. Construct a binary classifier for every possible pair of classes. So the OVO, so one versus one, means that for a data set with n classes, the method creates like classifier that we can see on the JAPO. So it's the formula that you can see. So this approach has a significant advantage because each classifier deals with only two classes, which makes the task simpler. However, the number of classifiers grows rapidly as the number of classes increases, making the process absolutely expensive for problems with many classes. So the steps for implementing the one versus one classifier are similar to those of one versus all classifiers, with a key difference. So when comparing the one versus one approach to the one versus all method, it is essential to consider the context of the problem. The choice between the two methods depends on the specific problem. The one versus one classifier is better suited for problems with a smaller number of classes, as it avoids the challenges of imbalanced data. About the key observations, in this exercise, we use two methods, one versus all and one versus one, to classify customers into their segments based on their shopping habits. Both methods gave the same result for this data set, but they work differently and have their own strengths and weaknesses. So OVA, so one versus all and one versus one, both worked well for this task. Choosing which one to use depends on the size of the data set, so the number of classes, and how much time and computing power you have. So one versus all is faster and simpler, but one versus one may give more detailed results, but takes more time and resources.
So for the performance metrics, when evaluating a multi-class classification model, we rely on specific performance metrics to understand its strengths and weaknesses. The most basic metric is accuracy, which measures the percentage of correctly classified instances across all classes. While useful, accuracy alone can be misleading, especially in balanced datasets, where the model might perform well on majority classes but poorly on minority ones. For example, if a dataset has 18% electronics and only 10% each for clothing and books, a model that predicts electronics most of the time might achieve high accuracy while failing to represent the small classes. To gain deeper insights, we use metrics like precision, recall, and F1 score. Precision tells us how many predictions for a specific class are correct. For instance, if the model predicts 100 instances as books and 18 are correct, the precision is 18%. Recall measures how well the model identifies a true instance of class. If 100 books exist in reality and the model correctly identifies 17, the recall is 17%. The F1 score balances precision and recall into a single value, particularly useful when dealing with imbalanced data. This matrix can be averaged in two ways. The macro average gives equal weight to all classes, regardless of their size, highlighting minority class performance. On the other hand, the weighted average accounts for the size of each class, reflecting the dataset's overall structure more accurately. To visualize performance, we use the confusion matrix. This tool compares actual versus predicted classes and highlights errors. For example, it might show that books are often misclassified as clothing, suggesting similar features between these two categories. Finally, analyzing these metrics helps identify areas for improvement, such as rebalancing the dataset, engineering better features, or adjusting model parameters. Combining these metrics provides a complete picture of the model's performance, ensuring it performs well across all classes and not just the majority ones. So for the step one, we import required libraries. The necessary libraries are imported at the start, including NumPy for numerical operations, decision tree classifier to build the classification model, trend test split for splitting the dataset and metrics such as precision, recall, F-score support, classification report and confusion matrix to evaluate model performance. The step two is the load and export the dataset. The dataset is loaded into a pandas data frame, and functions like head and info are used to explore its structure. This step ensures a clear understanding of the features, the target variable, and the presence of any data quality issues. The third step is to split the data. The dataset is divided into features X and the target variable Y, and then split into training and tests using an 80-20 ratio. Stratification is applied to maintain consistent class distribution across the sets. So we get this. For the step 4, train the decision tree model. A decision tree classifier is initialized and trained on the training data using the fit method. This process allows the model to learn patterns and decision rules from the datasets. So we have these results. For the step 5, we make predictions. Predictions are made on the test data using the point predict method. This step generates the predicted class labels for evaluation. For the step 6, we evaluate micro and macro averages. Precisions, recall, and F1 scores are computed using precisions, recall, F-score support. Both micro and macro averaging methods are used to evaluate overall performance and performance per class, respectively. For the step 7, we generate a classification report. A classification report is generated with classification report providing detailed metrics such as precision, recall, and F1 scores for each class, along with the number of samples in each class. And for the step 8, we plot the confusion matrix. A confusion matrix is created with confusion matrix to compare actual and predicted labels. To enhance interpretability, the matrix is visualized as heat map, highlighting the model's performance for each class. So for the step 9, we're fitting the macro averaging, the micro averaging using the precision recall F-score support function. And for the step 10, we're generating the classification report using the y-test and y-pred variables. So we have these results.
Okay, so now I'm going to talk about how machine learning can be applied to marketing, particularly focusing on a challenge called class imbalance and how we can address it. So let's start by imagining a company that uses the most popular communication channel to promote every product. So at first glance, this might seem like a good strategy, but after all, the channel is widely used, so it should reach a large audience. However, this approach can actually be ineffective for certain products. Some products may perform better on less popular channels that target a specific audience. So seeking to the most popular one could mean missing the right customers. And not only does this strategy risk wasting money on advertising, but it could also drive up costs without delivering the expected results. So this is where machine learning comes in. By implementing machine learning model, the company can move from a one-size-fits-all approach to a more tailored product-specific strategy. So with machine learning, each product can be promoted on the communication channel that best suits its target audience, making the marketing efforts more efficient and cost-effective. So now, why is class imbalance problematic? So when one class is overrepresented, the model will often become biased towards predicting the dominant class because it's been exposed to it more frequently, and this means the model could fail to properly predict the less represented class, which could be crucial. So to solve this, we can use techniques like SMART, synthetic minority oversampling technique, which helps balance the data set by creating synthetic examples of underrepresented class. This ensures the model has a better chance to learn to predict both the common and rare classes accurately. So in conclusion, class imbalance is a significant challenge, especially when one class dominates the data. However, by using machine learning and techniques like SMART, we can tackle this issue and improve predictions, whether we are optimizing marketing strategies or detecting fraud. So the SMART is a technique used in a machine learning to address the issue of class imbalance in dataset. So it works by creating synthetic samples for the minority class to increase its representation rather than simply duplicating existing samples. So this helps in mitigating the risk of overfitting and improves the model's ability to generalize. So when working with imbalanced dataset where one class is much less represented than the other, it's essential to apply strategies to prevent the model from favoring the majority class at the expense of the minority class. So the sampling technique, a way to address class imbalance is by modifying the dataset using sampling techniques. So the first one, the random undersampling. So here we reduce the number of samples in the majority class by removing some data points. So the advantage of this solution is training becomes faster, but the disadvantage is that informations can be lost, which can lead to underfitting. The second one is the random oversampling. In this method, we increase the number of samples in the minority class by duplicating data points. So the advantage is that there is no information loss, and the disadvantage is that this solution can lead to overfitting as the same samples are repeat. So now the third technique is SMART, so the synthetic minority oversampling technique. The SMART generates new synthetic samples for the minority class by implementing between existing data points. The advantage is that it will reduce overfitting while maintaining the original class distribution. And the disadvantage is that it's less effective for datasets with many features as high-dimensional relationship. They are harder to capture. So let's see one example. If we take one example to illustrate the impact of these methods, if we suppose that we have a data set where in the class 1, the minority has 100 samples, and the class 2, the majority has 500 samples. So we will see why the SMOT is particularly the most beneficial. It will reduces overfitting compared to random oversampling. So the random oversampling duplicates existing minority class samples, which can lead to overfitting, and overfitting happens when the model memorizes the duplicated samples instead of generalizing patterns. The SMOT generates synthetic samples by interpolating between existing minority samples and creating new data points that are unique and realistic, so reducing the risk of overfitting. There is also no information loss, unlike the undersampling, which removes data from the majority class to achieve balance. SMOT does not discard any data, so this is especially useful when the majority class contains important information. The SMOT is flexible and easy to use. It can be applied to a variety of machine learning models and datasets with minimal pre-processing. So the tools like imbalanced learn in Python make it straightforward to implement. So the practical application by using applying SMOT, the minority class will have a similar number of samples as the majority class, and this ensures fairer model training and improves the ability to predict outcomes for the minority class. So I'm gonna conclude because we we don't have so much time. So in conclusion, addressing class imbalance is essential for improving the performance of fairness of machine learning models, particularly in applications like marketing. Techniques such as SMOT provide an effective solution by generating synthetic samples for underrepresented classes, ensuring balanced dataset without information loss or overfitting risk. So by leveraging these methods, businesses can create more accurate, tailored strategies that will maximize efficiency, enhance decision making, and better serve all customer segments. So to conclude this presentation, multiclass classification is a powerful tool when dealing with problems where there are more than two possible outcomes. So by understanding different approaches such as one versus one and one versus all classifiers, we can tailor our models to handle multiple classes effectively. However, challenges like class imbalance can lead to biased models that favor the more common classes, potentially overlooking important, less frequent ones. So through techniques like SMOT, we can address these issues by balancing the data, allowing our models to perform more accurately across all classes. In practical applications such as marketing or fraud detection, using the right classification methods and ensuring balanced data can make a significant difference in model performance. And ultimately, a deep understanding of your data coupled with the right techniques is a key to achieving more accurate and meaningful results in multi-class classification tasks. Thank you.